So today we're going to start talking about independent samples for two means and looking at hypothesis testing when we're looking at two different populations. So in Chapter 7, we looked at 3 hypothesis tests. Each of these tests was a test for one population, either a mean or a proportion, depending on the test. There are many cases where we would like to compare two populations of interest, both of which have unknown population means or unknown population proportions. For today, we will limit our conversation to population means, right? We've already looked at proportions, so we're going to focus on means today. So there are two different hypothesis tests for two population means. So the first one, the hypothesis test for two population means where, right, the population standard deviation is known for both populations. And then there's a hypothesis test for two population means when the population standard deviation is unknown. And you may recall, right, that if we know the population standard deviation, usually it's a Z, right, test. And then if it's unknown, right, it is a T test. And there are some assumptions we do need to look at, but just in general, those are sort of the two different distributions that we look at. So our basic idea of a hypothesis test for two population means, right? So we have population 1 with some mean and population 2 with some mean. We take two samples, not necessarily the same size, right? So I have population 1 with its population mean and standard deviation, and then population 2 with its mean and standard deviation. I take a sample of it, that's N1 and that's N2. And we can calculate the sample mean and sample standard deviation from each of the different samples that we took. And so we have X bar sub 1 and S1 from the first population, and X bar sub 2 and S sub 2 for the second population. And again, right, those are sample means and sample standard deviations. So the table just gives sort of an outline of the different things that we get from taking the sample, right? N sub 1. So let me highlight as I'm talking, right? So N sub 1, X bar sub 1, S sub 1, right? So sample size, sample mean, sample standard deviation for both of the different populations, right? So it then goes on and says, in a hypothesis test for two population means, we are no longer testing that one population mean is different, greater or less than some specified value. Instead, we are now comparing the two means to one another. So my null hypothesis, right, we would say the mean from population 1 is equal to the mean for population 2. Now, if we rearrange this, sometimes we'll see mean 1 minus, right, mean 2 of the different populations is equal to 0, right? Another way that you can see it. Now, again, we have 3 alternative hypotheses to choose from, right? The not equal to, greater than, less than. So I have, right, again, the population of mean 1, population of mean 2, we could say is not equal to. We could say that the mean of population 1 is greater than the mean of the population 2. Or, right, the last one, the mean of population 1 is less than the mean of population 2. And just like we saw with the different inequalities, right, not equal to is a two-tailed test. We have greater than is a right-tailed test, so right-tailed, and then less than is a left-tailed test, right? So what we saw before still applies here in terms of the inequalities. Now, our assumptions, right, we do have some assumptions we want to check. So it says a random sample of size, right, so N sub 1 is taken from population 1, right, so the biggest thing here, right, is it's a random sample. So a random sample of size N sub 2, right, from population 2 is taken. Note, the samples do not need to be the same size, but the test is more robust if they are. B is the two samples are independent, right? We looked in our last section about dependent samples. So in this section, they do have to be independent. C says population 1 is normally distributed. Also, population 2 is normally distributed. Just as before, the t-test is fairly robust to the assumption if the sample size is large. This means that if this assumption isn't met, but your sample sizes are quite large, over 30, then the results of the t-test are valid. So if we're taking large enough sample sizes, then we should be good. Now, D says the population variances are unknown and not assumed to be equal. The old assumption is that the variances are equal. However, this assumption is no longer an assumption that most statisticians use. This is because it really isn't really realistic to assume that the variances are equal. So we will just assume the assumption of the variances being unknown and not assumed to be equal is true, and it will not be checked. So let me highlight a couple things, right? So variance is unknown. Now, if you recall, it's been a while since we talked about variances, but sigma squared, right, is variance. And we're basically saying sigma, the variance of the population 1 is not equal to the variance of population 2. So what this means, right, it has to do with what we call pooled or not. So we're assuming they're unknown and not equal. So we are going to be using for all purposes a 2-sample t-test. I do show and talk about a z-test, but we're going to focus on the t-test. So again, it says if you know the population standard deviations, we'll use a 2-sample z-test. If you do not know the population standard deviations, we'll use a 2-sample t-test. And this is the one we're going to use. If you think about it, if you don't know the population means, you probably don't know the population standard deviation. So why we usually just use that 2-sample t-test. So the distributions, test statistics, and degrees of freedom, if necessary, formulas are below. I did list out the formulas. We're going to go through and have our calculator do this by hand, but they are here in case you need it. So you can see it looks similar to what we saw before. The biggest thing, right, is remember that this piece here, right, mu, the population mean from population 1 minus the mean of population 2, right, we're saying that this is equal to 0 all the time, right? We're saying that there's no difference. And you can see the standard deviations in the sample size. Our degrees of freedom is a little crazy here. So the calculator actually does give you this degrees of freedom if we needed it, but there is a formula how you can find this. So this is the one we're going to use for our hypothesis test, but I did want to write out the z-test just in case you can sort of see it, right? There's no degrees of freedom in this case, and it looks really similar to the one above, right? Just not with the degrees of freedom and with the population's standard deviations, or I should say the variances because they're squared. All right, so we've overlaid sort of what we're going to look at when we do these hypothesis tests, and in our next video, we'll actually go through and do our first example.